I'd give it a second. You know. All right, ladies and gentlemen. This class recording has started as this is take 3 really. So it's good. All right. Yesterday we introduced this idea of projectile motion, and we talked about, we did the demonstration actually the other day about the two motions being independent of one another. But yesterday we focused a little bit more on the idea that when we are analyzing projectile motion, we have to analyze the two dimensions separately, or the two axes separately. That we can look at the position versus time equations for each dimension separately, right? X position, Y position, but there's two separate equations because they are separate from each other. And at the end of class yesterday, we did this example problem where the guy was skateboarding along and dropped the basketball, and then we used how far or how long it had been dropped after, like, the 0.25 seconds, and other things about that motion to figure out where the object was at that time. If you would please open up to page 146 of your book, page 146. And on page 146, you will see, nope, not that one, problem number 85. So, page 146, problem number 85. So, it's a problem about baseball because the World Series started yesterday, much to Miss Dietrich's chagrin, but whatever. All right, so it says, playing shortstop, you pick up a ground ball and throw it to second base. The ball is thrown horizontally with a speed of 22 meters per second directly towards point A, as shown in figure 4.37, which is right there. When the ball reaches the second baseman, 0.45 seconds later, it is caught at point B. So two parts. How far were you from second base? What is the distance of the vertical drop from A to B? So we said that in solving these problems, to keep our information organized, what we have, what we're looking for, I recommended that you start off with this 3-column table. And one column will take care of the horizontal stuff, one column will take care of the vertical stuff. And when we talk about the stuff, right, those are all the things that we have discussed up until this point that we can use to describe and represent motion. Just because we've gone from one dimension to two dimensions doesn't mean that we don't use the same idea. So, we talked about knowing where an object starts, both on the x-axis and the y-axis. Where that object ends up, both on the x-axis and the y-axis. What was it doing initially on the x-axis and the y-axis? What is it doing ultimately on the x-axis and the y-axis? Was it accelerating, and for how long does this trip take? Okay. So those are the 6 things that we've introduced over the course of Chapter 2 and Chapter 3 that we're now applying to 2 dimensions. All right, first things first. We need to determine what we are looking for. So what are we looking for in this problem? 2 things, actually, right? Okay, go ahead. The final position, right? Final position, right? If we talk about how far away we are from the second baseman, is that X or Y? Yep. That's going to be X. So how far away is the final position here, right? And then distance of the vertical drop, it even tells you in the problem it being vertical, right? That's what it wants us to figure out. Okay, before we start analyzing these things, right, all of the descriptions of motion that we've discussed up until this point depend on reference point, coordinate system, etc., etc., etc. Here in this problem, it doesn't give us the reference point or the coordinate system like it did in the previous problem. That being said, we can pretty much choose wherever we want to put it. I think in this problem, to me at least, and if it doesn't make sense to you, that's okay, but it doesn't really matter. To me, I think it makes the most sense to put my x-axis here and to put my y-axis there. The point where the shortstop releases the ball then would be our origin, right? Good there? All right, so now that we've got that, we can start filling in some other things in the table that will help us get to our ultimate goal. We said that there were two things that we could fill in right away, right? What are the two things that we can fill in even without reading the problem? The acceleration y is going to be what, kid? This is going to be 9.81 because what's affecting it vertically? Okay, and in this case here, right, if we called the spot where the shortstop threw the ball the origin, gravity's acting which direction? Downward, which would be which direction on the y-axis? Usually that's going to be negative, and we'll keep it that way there. Okay, and then the other thing that we can fill in, acceleration on the x-axis is going to be what? 0, because there's nothing else besides gravity that is affecting that object. Okay? All right, now some things specifically to this problem. Brett, do you have a question or do you want to fill some more in? Okay, go ahead. Yep. Hold on to that question just for a second because that's part of the wrap up to this question. Okay? All right, so those are the two things we can fill in right away. Other things we can start filling in. What's the initial position of this ball? We made it the origin, right? Meaning that x initial is going to be 0, and y initial also going to be 0. Okay? What other information did they give us to work with? Okay, they gave us a velocity, right? Luke, what does it tell us about that velocity? Okay. In this case, it says it's 22, but because it says that we've thrown that ball horizontally, right, that's going to be our initial velocity on the x-axis. Like we discussed yesterday, if we throw it horizontally, at the very moment that it becomes a projectile, it is moving horizontally, but it is not moving vertically. And if it's not moving vertically at that very moment when it becomes a projectile, that is going to be 0. We refer to this problem as a horizontal launch problem because it becomes a projectile when going horizontally. But like the picture shows us here, it won't stay on that horizontal path because gravity starts affecting it and starts pulling it down. Okay? All right, good there? One more thing that we can fill in our table here. What other information did they give us? They gave us the time. Yesterday, what did I tell you about time? It's pretty important as far as solving these problems go. Happens at the same time, meaning what's true about the time horizontal and the time vertical? They have to be the same. Always, always, always. So this is 0.45. And this is 0.45, okay? Because those two horizontal and vertical motions occur simultaneously, those times have to be the same, okay? Good there. All right, then going back to our packet, right? Position time equation for projectiles. We have a horizontal equation and we have a vertical equation. Those equations both apply to this problem, right? Okay? But then, knowing what we know about some of the information that they gave us in the problem, some of these terms go away, right? We said the initial position on the x-axis is 0. The initial position on the y-axis is 0, but then also the initial velocity on the y-axis is 0 as well, so this whole term is going to be 0 too. Okay? Now we can start plugging in things that we know into this equation and figure out what is the final position on the x-axis, final position on the y-axis. So, if you haven't started doing that already, go ahead and do so. Go ahead, Brett. Oh, is this 9.9? And this one is negative 0.99? Right. That's one that that's one that you should probably, if you can remember that one shows up kind of a lot. So, all right, are we good with these two? Good with these two answers here? Questions? We need a couple more seconds to finish off. All right. So, Brett, back to your question. Okay. On page 3 of your packets, the top part talks about the path that projectiles follow. And like it says, projectiles follow parabolic paths. We have two motions that are occurring simultaneously. We have a horizontal motion and a vertical motion. Looking at the equations, the horizontal motion gains position at a linear rate because all you've got is t in that equation. So it goes 1 meter, 2 meters, 3 meters, 4 meters, and it always takes the same amount of time to go that extra meter. But in the vertical equation, you have a t squared term. So you don't have the two motions gaining at the same rate. One is picking up distance faster than the other one. It's gaining distance vertically faster than it's gaining distance horizontally. That results, if we have two variables and one is changing at a different rate than the other one, that gets us a parabola. That's how we get a parabola. Now, the curvature of the parabola depends on a couple of things. The biggest thing that it depends on actually is the horizontal velocity. Because vertically, it's always going to gain at the same rate because gravity causes it to gain distance on the vertical axis. So the curvature of this parabola really depends more on the horizontal speed than the vertical speed. Here, let me do this. Like it says here, right? Horizontal motion is uniform, equal distance in time. But if we looked at the vertical positions, they keep getting farther and farther apart because it's accelerated. The curvature of this parabola really depends on how these things are spaced out. A parabola or a projectile motion that has a small horizontal velocity would look like that. But a projectile motion that has a large horizontal velocity would look like that because it goes more horizontal distance. These would all take the same amount of time. It would take each one of these things 0.505 seconds because that's determined by the vertical motion. How long does it take to get from 1.2 to the ground? And that would be the same time as if we just dropped it straight down. Every single one of those paths would take exactly the same amount of time. But the path that it takes, being a combination of the two of them, that's determined more by the horizontal motion than the vertical motion. Yep. No. Regardless of what the horizontal speed is, as long as they all start at 1.2 meters above the ground, they will hit the ground in 0.505 seconds. It goes out further because red is going faster horizontally than blue or dark blue or purple. Remember, it's covering horizontal and vertical distance at the same time. So the faster it's going horizontally, the more horizontal distance it will be able to occur, or it will be able to cover in this 0.505 seconds. They would be spaced out more, yes. Like these dots up at the top, they would be spaced out more, but there would be the same number of dots because that represents the time factor going by. And in the, at risk of launching us into a discussion that we had on Friday, right? If this is fast enough, right? If that's fast enough in the amount of time that it takes this object to drop the 1.2 meters, the ground can curve 1.2 meters as well, and now we haven't gotten any closer to the ground even though we've gone in that parabolic path. Not because it takes longer, not because the green one takes longer, but because the ground just isn't there anymore. Okay? Good there? Next part of your packet, also on page 3, deals with velocity. The last example that we did, and the example that we did yesterday, shows how position is independent x and y. That we can look at both of them separately. It doesn't really matter, that they're happening simultaneously. We can look at each of them individually. The same is true of velocity. This equation So this equation up at the top hopefully looks familiar. We introduced it back in section 3.2, right? But again, applying it to the projectile motion, we have an x equation and a y equation. But now, if we then get specific about what we're talking about, right? What did we say the acceleration on the horizontal axis always is? 0. Meaning that this term in the horizontal version of this equation goes away. And the final on the horizontal axis equals the initial on the horizontal axis. Meaning, what's true about the horizontal velocity? It's not accelerating. Not that the velocity is 0, the acceleration is 0. What would we say about the horizontal velocity? It's constant, right? So if we know either the final horizontal velocity or the initial horizontal velocity, we automatically know the other one. Because the only thing affecting it, the only thing affecting the projectile is what? Gravity. And gravity only affects things vertically, not horizontally. That would be our assumption of no air resistance. In the problems that we're going to do in this section, you can make that assumption. Okay. But, right, in the second one, right, there is acceleration. It's caused by gravity. Okay? So we'll substitute in g for that spot in the equation. But remember, the equation is VI plus AT. Here they kind of take the liberty of making it minus, assuming we'll call down the negative direction. I would rather you guys have this as a plus sign, right? And then we'll make it minus depending on the coordinate system for our problem. All right, good there? Okay. On page 4 of your packet, you have quick example 4.10. What's the speed in each direction? Which is right here. So it says, you throw a baseball from the roof of a house to a friend on the ground. First, a couple of public service announcements, right? 1, it's dangerous up on the roof. Okay, just be careful. 2, it's even more dangerous to throw things off of your roof towards people on the ground. Right? Just keep that in mind. I'm safe, right? It's dangerous to throw things. Some may be more dangerous than others, but it's still dangerous to throw things. It says the ball has an initial velocity of 12.0 meters per second in the horizontal direction. After 1 second, how fast is the ball moving in the X direction and in the Y direction? So, because there is no picture, I will draw a picture. All right. So there you are. All right, I wanted to make it something different colored, just so we, so. And maybe it's actually. Wait, hold on. Now it's a softball, so it's a high vis softball, right? Then there's another person down here, right? How's that? Okay. They're a Royals fan. I'm lucky for them. So, all right. So you throw the baseball off of the roof with an initial velocity of 12.0 meters per second in the horizontal direction. We just talked about the idea that even though you throw it horizontally, what's going to start happening to it? Gravity's going to start acting on it, and that will cause it to travel in what kind of a path? A parabolic path, right? Okay? Let's say that this spot, oh, come on. Sorry, buddy. Really thought I'd be able to, okay. Let's say this spot right here, that's where the ball is 1 second after we threw it. Doing this problem, we should start exactly the same way as we started the other problems, right? Those are the 6 things we've talked about. Horizontal side, vertical side. What is this question asking us for? Final velocity, right? If it says after and how fast, put those two together, that means final velocity, right? In the x direction. So there's one of our unknowns, and then in the y direction, there's our other unknown. Okay? All right. Next, where do we go? Acceleration. Acceleration in the x direction is always 0. Acceleration in the y direction is 9.81, sign dependent upon our coordinate system, right? Luke, where do you want to make our reference point in this problem? Probably a good idea. Not necessary, but we can pretty much make it wherever we want, right? So, there's our x-axis. There's our y-axis, not straight. Okay? So that means that if we make this our reference point, right? Those are going to be true, and that's going to be negative. Okay? All right. Other things we can fill in. Time. What has to be true about the time, Luke? Okay? And then one more thing that or actually two more things we can fill in, right? Okay? It says initial velocity of 12 meters per second in the horizontal direction. This is 12 meters per second, but if it was thrown horizontally, what does that mean about our, oh, sorry, hold on. Nah. Are you kidding me? Oh. That's 12. But if our initial velocity in the horizontal direction is 12, go right. That has to be 0. Okay? All right, good there. Okay? So, let's go about answering this question. One part A of this question is super easy. Okay? What did we say has to be true about the initial velocity horizontal and the final velocity horizontal? They have to be equal. Why? Because what's the acceleration on the horizontal axis? And if acceleration is 0, what's true about the velocity? It's constant. So this has to be 12 meters per second. Then, on the other side, right, we just learned this equation. Okay? Knowing that our initial velocity is 0, right? That gets rid of that term. And then, oops, sorry. All right, we can make that g because that's the acceleration value that we're dealing with, right? 9.81. That being the case, right, the time they gave us to work with was 1, so this becomes a pretty easy problem, hopefully. Okay? Good there? Okay. Now, the next part leads us into practice problem number 38, which is right below that example in your packet. We just calculated that this object is moving 12 meters per second horizontally and 9.8 meters per second vertically. 38 asks us for the speed, which is how fast. Remember, while these two dimensions are happening simultaneously, while they do not affect each other, they are independent of each other, but they are acting simultaneously. Meaning, there's a horizontal motion and there's a vertical motion, and if we want to know how fast this object is going, we have to take into account both of them. All right? Luke sees where is this going. Anybody else see where this is going? Well, you've got a vector that's horizontal, and you've got a vector that's vertical, and we have to find the combined result of both of them together. What are you going to do? Say again? Don't say it. Don't say it. All right? Okay. Purple represents the speed of that object. It is the resultant of the two velocities. Remember, we started off this unit talking about vectors and finding resultants, and most of the time we were dealing with displacements, but we can find the resultant of any two vector quantities. It just so happens in this case we're finding two velocities. We know that this is 12. We know that this is negative 9.81 because it points downward. But in order to find purple, in order to find purple, what are we going to have to do? Pythagorean theorem, right? So does it matter that this one's negative? Because what are you doing to it anyway? You square it anyway. All right? So we can find the hypotenuse of this triangle, and that will get us the speed of the ball at that moment. Brett, is that what you wanted to do? Or did you have a question? No, okay. All right, good there. Okay, tonight, if you guys look on the calendar, Tuesday night's homework, you guys are ready for at this point in time. You really weren't ready for the homework last night because we didn't really get that far. But if you go to Tuesday night here, the 21st, and pull up this horizontally launched projectiles, right? These are the questions that at this point you should be able to answer, okay? The answers are posted here, so if you want to check out and see how you did, it will be there for you, okay? Good? Questions? All right, tomorrow we will get into launching things at an angle and throwing things up into the air, right, as opposed to just letting them like roll off the edge of the table. So, yeah, we're stepping it up. So.